The Unit 7 reader has a bunch of important information. Now, um, um, I always expect you to read the reader. It's like the book. And I always rush through these study goals because it's at the end of the unit and they're usually afterthoughts, like something that your book didn't really talk about. And when I tell you what to look for, I'm just trying to guide you in adjusting where you focus your attention, but I still expect you to read these articles, okay? In number 37, there's this concept which might be new to you, the idea of environmental regulatory functions. That's a public service function or a natural service function. So something that nature does for free, like thank you nature for helping me with this. You know, like forests regulate the atmosphere because they soak up CO2. The ocean regulates global temperature because it's a huge heat sink. So, you know, it's like having a water bed, doesn't get too hot, doesn't get too cold. You don't even know what water beds are, huh? Anyway, it's a place for heat to be stored. So it's like a buffer. You know, it's like being in an adobe house. It doesn't get too hot, doesn't get too cold because there's a place for all the heat to go. The ocean does that, specific heat capacity of water. It also absorbs and regulates gases from the atmosphere. So that keeps the atmosphere gases from spiking too much, because when there's a lot of extra, they go into the water, and when those gases are very low, they come out of the water. You know, the same way that the water in your lungs sort of averages out oxygen and CO2 to the atmosphere when you're breathing, concentration gradient. Number 39 is just vocab. Phyto is plant stuff, zoo is animal stuff, and plankton is any living thing that can't move on its own. That's just vocab. I guess you got it there. You don't need the article. I want to highlight calcium carbonate. So anything with a hard shell in the ocean, that hard shell is made of calcium carbonate. By the way, so are our bones. And those hard-shelled things in the ocean, like seashells, oysters, coral, that's a place where carbon is sunk. So CO2 in the air becomes carbonate ions in water, and carbonate sticks to calcium to make shells in the ocean. Calcium carbonate is a carbon sink. This eventually becomes sand, and that becomes limestone and marble rock. In other words, atmospheric becomes hydrological, becomes biological, becomes lithospheric, long-term storage. Number 42, just introduced 4 words, use the article to define them. That's the 4 words. And you should know that sometimes these can be used for the ocean. Not often, but people do use these for the ocean. Number 43 is just a national average of water distribution, and it's a little bit outdated, but it's interesting to see where things rank. And yeah, toilets are the #1 water user inside a home. That's still accurate today, even though we have more efficient toilets. It's still the #1 water user inside a home. So you should definitely know that toilets is #1. Can you imagine we do all this work for fresh, clean drinking water? All over the world, people are dying because they can't get drinking water, and we use that drinking water first and foremost to flush our turds. Isn't that shocking? It's important to point out that where you and I live, our primary use of drinking water is outside. We all want to live in Scotland, so we want to be surrounded by grassland, but grass doesn't grow in the desert, so we're a bunch of idiots for growing grass. By the way, everybody wants to be a farmer, so like me, people have fruit trees all over the yard, and I should point out that I use recycled water to water my fruit trees. I have a modified water system, so all my showers and laundry are used to irrigate my yard. I don't use drinking water. But anyway, most of us use a ton of water outdoors. I want to remind you that wastewater is fertilizer because it's productivity in reverse. Instead of going nutrients to compounds to biomass, that's productivity. Wastewater goes from biomass down to compounds, down to nutrients. So that's essentially fertilizer water. That's why we can use our wastewater to irrigate athletic areas and parks, and that lowers our need for fertilizer because the water already had nutrients in it. Think about it, all the nutrients of life are in our diet, so our waste stream has all the nutrients of life when you go backward. In number 45, it's interesting to point out that fish are different. In cold water, you need ladders for fish to get up over a dam. Cold water fish have a lot of oxygen in their water, so they're really hyper. Salmon are aggressive, fast swimmers. They swim up those puddles. Those are called salmon ladders. That's cold water fish. Warm water fish have less oxygen in the water, so they're chilling. They move slowly because they're relaxing in the warm water. So instead of going up, they go around. That's called a bypass canal. Warm water migration is different from cold water migration. Cold water fish go up a ladder. Warm water fish go around the dam to get upriver. So in warm water parts of the world, they don't do ladders. They do canals around the dam site. Our reservoirs are pretty rad. We have a bunch of surface reservoirs like Kachuma, Gibraltar. Those are just, regular dams. But we've got a really neat one up in North County where most of the water is used for irrigation of farms. So there, instead of storing water in an above ground reservoir, our county bought a huge flat area surrounded by mountains. And they just bought this one farm called the Twitchell Reservoir. And it's not a reservoir. When you go there, it's just sand and some grass in the winter. But what happens is all these mountains fill this valley and that soaks into the ground. So it's a reservoir for groundwater recharge so that people in Guadalupe and Santa Maria can extract the groundwater to run the sprinklers on strawberries and other agricultural products. Kind of rad. It's pretty rare that people would have purchased a groundwater recharge reservoir, but Santa Barbara did. Number 47 tells you about it. Number 48, you should read about this, but salmon are used to flood season. And of course, when it's raining, we fill the reservoir. So what they do at Lake Kachuma, my buddy's in charge of this, is at specific times of the year, they will open up the reservoir and let flood waters go out the Santa Ynez River so that steelhead can come up the Santa Ynez River. That's pretty cool too. We have seasonal release of water to accommodate salmon migrations. You should read about this in 48. Number 49, we talked about desal in a previous study goal, so I'm assuming that you already have these notes. Number 50, I think we already discussed this, right? Reusing water saves drinking water because you don't have to use drinking water for irrigation. But you should know that in Santa Barbara, that's what the purple pipes are. Like if you ever see a big water project, especially at the high school, where you see purple pipes, you don't drink from that because that's reused wastewater. Let me see here. For number 52, I probably didn't have to put this in the reader because we already had a good lecture about virtual water consumption. For 53, building a dam is pretty expensive, but taking it apart is extremely expensive. Like when you're building a dam, you dump concrete downhill. But if you want to take it apart, you have to pull concrete against gravity. So huge chunks of concrete have to come out, and that's really slow, labor-intensive, dangerous, and expensive. Also, you got to find a place to put all the sediment. Remember that because the water slows down, reservoirs fill up with sediment. And there's a lot of dams that we can't take apart because we can't find a place for all that sediment. Like the Matilaha Dam near Ojai in your backyard, we've got a dam that we can't get rid of because we can't find a place to put the sediment. There literally is not enough land between the Matilaha Dam and the ocean. There isn't enough land for that sediment. There's no place literally to put that sediment. Really big reservoirs fill up at a rate of up to 2 trash trucks per second. So you can imagine you'd have to be driving all these trash trucks out at more than 2 trash trucks per second. That's a lot of sediment we're talking about. And of course, people who have now moved in below a reservoir, their property values are really high because they have riverfront property. And now those values would go down because they might get flooded in the absence of a reservoir. So there's a lot of property value struggles. Now that we have already built the dams, it's almost impossible to get rid of them. And very recently, I believe yesterday, a huge deal was signed to get rid of a bunch of dams, a whole cluster of them on the Klamath River, which is up in Northern California. And so if you're interested, you might want to look into this deal about decommissioning dams on the Klamath River. Klamath is spelled on the screen here. Number 54, I want you to remember sediment in water is both a good thing and a bad thing. So it's good when an environment normally has sediment, right? Like if the ecosystem has evolved in the presence of sediment, then sediment will be a requirement of that ecosystem. And it's bad if your environment has evolved without sediment and now you're adding more than that environment is used to. You know, species evolve in one set of circumstances. You can't just change those circumstances. So there's sediment in a good sense and sediment in a bad sense. What's interesting is in the Colorado River, there's always been huge volumes of sediment. Think about it. You're hosing off the desert every time it rains, right? Colorado River, desert, Colorado Plain, sand. So whenever it rains, you're just washing the desert into the river. And so those rivers have evolved in the presence of sediment. There's a whole bunch of species that evolved in the Colorado River to take root in the sediment that piles up on the turns of the river. Now, when we add dams, we block that sediment supply. So downriver of the dam, it gets really rocky because all the sediment is filling up the reservoir, right? So something fascinating happened. They tried an experiment at Glen Canyon Dam of letting a flood of sediment out on purpose. They had to do some fancy plumbing to accelerate the water right at the bottom of the reservoir to get a whole bunch of sediment into suspension. And when that muddy water was released down canyon, there was this like massive ecological revival. You should read this story. It built up the shores. It made sandbars so plants could grow. So there was all this organic material that fertilized the soil. So all these species that hadn't been seen in a long time started to grow again. And all of the consumers that are built on top of those plant species started to show up again. So insects had a revival, which brought in more fish and more birds. And remember, the takeaway is if a river is used to sediment, then you want to maintain sediment flow. You should read this article. It's number 54. In number 55, the distinction is that dams change the water conditions or the ecological conditions for native fish, whereas in other parts of the world, dams changed the route of migration for migratory fish. Remember, I expect you to read your reader, but that was a review of the reader goals. I'm going to stop this recording.